solids and gases. Chapter 10, talking about temperature and a little bit about the kinetic theory of gases. All right. So we're going to introduce that today, and then tomorrow I'll be doing, maybe even today I can do some problems, but tomorrow I'm going to be doing quite a few examples on chapter 10. That means that we're going. Okay, guys. So chapter 9, as you just saw, it was all about the study of fluids and its behavior according to density, pressure, parameters. We studied the behavior of static fluids and just now fluids in motion. But there is another parameter that we can now introduce to study especially the state of matter of gases. Okay? So in this chapter 10, we are first going to introduce the idea of temperature and how a change of temperature affects solids, okay? And then we're gonna go into the kinetic theory of gases by introducing or by physically sort of reintroducing to some of you the ideal gas law, okay? And then towards the end of class, we're gonna be doing some examples with temperature, with some of the kinetic theory of gases, ideal gases. So if you have taken, and most of you have, chemistry class, right, Chem 1, you will recognize some of the parameters and some of the equations. The difference is the units, we use more metric system, right? So joules, kelvins, meter cube for volume, right? Kelvin for temperature. And since we're using joules for work and energy, then the universal constant of gases, the R value, is different, right? In terms of like the value, the way we use it. Other than that, is the same idea that you guys have done in the past. So let's start by introducing the zero law of thermodynamics, all right? Which, by the way, is going to be the last chapter that we're going to be doing on Tuesday next week. Yeah, that's the last chapter, thermodynamics. So you have a thermometer there, right? So the temperatures of A and B are measured to be the same by placing them in thermal contact with thermometer object C. We call that the temperature of equilibrium. So C and A are in equilibrium, and they both are at temperature of 22.5. Let's suppose that's Celsius. And C and B are also at equilibrium, thermal equilibrium, and that's 22.5 as well. So no energy is exchanged between A and B. So they both are at thermal equilibrium. Basically, if A and C are at thermal equilibrium, and B and C are at thermal equilibrium, A and B are at thermal equilibrium. That's the zero law of thermodynamics. And there is only, one of the consequences of this is that there is only energy exchange when there is temperature difference. And you know that from hot and cold definitions, right? How do you measure, or when we talk about an object being hot and another object being colder or cold, is because their temperatures are different. And be careful, guys. Temperature is a parameter for heat, and we're going to be doing that later, right? Some of you saw it yesterday, the MC delta T. But temperature is not heat. Temperature is a measure of the kinetic energy of particles. You see, every solid, every object, right, is made of atoms. And we can, I see here, yeah, I erase it. Ay, caramba. And we can let's just use this. So what happens is that every object is made of atoms, and you can visualize a solid as atoms connected by springs, right? Pretty sure I had it here. Oh, there it is. So if you increase the temperature of the solid, the vibrations are going to increase. You are increasing the energy. Ergo, you are increasing the kinetic energy. So temperature is just a measure of the kinetic energy of atoms. The more motion, the more energy, the more temperature. So for example, in here, right, you have two thermometers. One has a Bunsen candle at the bottom. So it's heating up the water, the container and the water, which is read by the thermometer. All right? And guys, if you have ever seen, some of you saw it yesterday, when you were boiling water, you see motion, you see bubbles. That's the motion, right? What's creating that motion in the liquid? The kinetic energy. The particles are moving at a greater speed, right? And we can calculate the total and the average kinetic of a particle, at least in a gas. You see, gases, especially ideal gases, are made of particles moving in random directions. And the characteristic of an ideal gas is that those particles, the distances are enough, so they are moving in random directions, but also they have collisions with a container, right? They have elastic collisions with a container. So there is no loss of energy. And you know already that in collisions, there is conservation of momentum. So that's how we define temperature. And eventually, we define heat as an overall amount of energy exchange between a warm object and a cold object. Heat is the transfer of energy from hot to cold. I'm going a bit ahead, but some of you probably already know about that, right? So, what temperature scales do we use? Well, in daily life here in the US, we use the Fahrenheit. But in engineering and science, there are two scales that we use. We use the Celsius, which you see here, and we also use the Kelvin scale. So in here, you have a plot of pressure versus temperature. And there is a linear relationship, right? The more pressure, the more temperature, right? That makes sense, right? Pressure is force, more energy, more temperature. I mean, kind of, right? Correlates. So in different trials, when you extrapolate the pressure at the zero temperature in those lines, they all converge at a value of negative 233.15. We call that the absolute zero in Celsius. Negative 273.15 is the absolute zero in Celsius. So therefore, we define the Kelvin scale. The Kelvin scale is the Celsius scale plus 273.15, because this is Kelvin here. It will be TK. All right. So we use that in gases. In the ideal law, we use that. But in daily life, or even in labs, we normally use Celsius, right? So where do we use kelvins? In astronomy. In astronomy, we use kelvins. For example, the temperature of the core of the sun is about 10 million kelvins, which, because it's so big, is also about 10 million Celsius. It's the same. However, the surface temperature of the sun is about 5,800 kelvins. So in Celsius, that will be 5,800 minus 273.15. Okay? So we use Kelvin scales in astronomy, astrophysics, right? The temperature of the cosmic microwave background, right? Which is basically this map that allow us to see the energy and temperature fluctuations of the universe, right? And we have used that to in some way or form, not some way or form, that's a proof of the Big Bang, of the expansion of the universe. So basically, now we know that the average, right, the average temperature of the cosmic microwave background radiation is about 2.73 kelvins, very close to the absolute zero. Right? Now, typically, students will ask, well, why is the universe so cold? If we can even say that, right? Because weird, the universe is really, there's no matter in the space, right? It's empty space, it's vacuum. But we can still measure this type of radiation using the Planck curve, the black body radiation. And we use that to also measure temperature of stars. So then the question is, if the universe is filled, space is filled of stars, why is the universe so cold? And the answer is easy. There's more empty space than what you actually think, right? The universe is expanding. Right now, probably we estimate to be expanding at almost the speed of light. So the distance between stars and galaxies are humongous. So there's a lot of empty space out there. And as the universe expands, it's cooling down. And that's why. All right. It's a simple explanation, but that's the reason or the logic behind it. So using temperature in kelvins, we can estimate temperatures of the frozen water, the surface of the sun, liquid hydrogen, liquid helium, right? In kelvins, it makes more sense. And here we have the conversion between different scales. So like I said, we use Celsius, Fahrenheit, and kelvins, right? Why do we use Celsius more in real life or in science and applications? Because the freezing temperature of water is 0 degrees and the boiling temperature is 100 degrees. So you can divide a thermometer in 100 equal units. That's 1 Celsius, like a ruler, right? However, in Fahrenheit, the frozen temperature of water is 32 and the boiling is 212. So we know that there is a conversion between, or there is a linear relationship between Celsius and Fahrenheit, and you're seeing it right now in front of you. The temperature in Celsius is 5/9 the temperature in Fahrenheit minus 32. So let's show you, right? Let's find the temperature, the boiling temperature of water using that conversion. So temperature in Celsius over 5 is temperature in Fahrenheit minus 32 over 9. That's another way of writing it. And I know that if my temperature of Fahrenheit is 212, that's the boiling temperature of water. Let's find it, right? Celsius over 5 is 212 minus 32 over 9. 212 minus 32 is 180 over 9. And that's 20. So temperature in Celsius is 5 times 20, 100 degrees Celsius. All right, so that's how you can use that. And then you can find the temperature variations. So my temperature variation in Fahrenheit is 5/9 my temperature variation on Celsius. Oh, sorry, 9/5. 9/5. So that means that in a day of summer, right? Let's suppose you are going from 85 to 75. That's a 10-degree Fahrenheit difference. That will be about 5 degrees Celsius difference, right? 10 divided by 9 times 5. That'll be more than 5 point something. Okay? So That's a nice equation there to figure it out between scales, the temperature variation or temperature difference from Fahrenheit to Celsius. All right. So we use both, mostly Celsius, when we're talking about uh, applications, but in problems, depending on the type of problem, we use Celsius or Kelvin. So for solids and liquids as well, right? What's an effect of temperature difference or temperature variation? It's basically, you have two examples in there, right? You probably have heard about railroads, separations, vertical joints filled with soft materials, right? And why do we do that? We do that due to thermal expansion. You see, in a very hot day of summer, metal or any element, right, depending on a coefficient that I'm going to show you, it will expand. And when the day cools, right, at night, it will contract back to its original length. So whenever we're building roads or walls, we have to take that into consideration. Also, when they freeze during winter, right? When we build a bridge, right, we have to take into consideration the frozen temperatures, right, which are going to cause contraction and thermal expansion during hot day of summer. And why do objects expand and contract? Because of a change on temperature. So we define thermal expansion like this. The change on length is equal to a coefficient alpha times the original length times delta T. Guys, delta capital T from now on is change on temperature. Time is labeled with a lowercase t. And you probably have noticed that when I do problems. The only thing here that you have to be careful is that capital T is also used for period. So you have to be careful with that. All right. And like I always say in physics, we do end up running out of variables. There are so many physical parameters, right? Density, area, length, period, time, temperature, mass, volume. Next semester, when you do current, right, we use the same variables. So it's about not just memorizing, but knowing what you are talking about. If you're talking about heat, thermal expansion, temperature, delta T is temperature change. But if you're talking about motion, oscillations, circular motion, capital T is period. Right? So, and then, just so you know, I is moment of inertia, right? Next semester, when you guys do current, I is the symbol for current. But then, how do you know? Well, because you're talking about circuits. So I cannot be moment of inertia. It has to be current. But when you talk about rotation, right? We talk about I as moment of inertia. So that's how you figure these things out. All right? And by the way, here it is. So look at the coefficients of expansion. We have for fluids and we have for solids. Aluminum, gasoline, mercury. So remember I was telling you guys about the problem that we did with a column of mercury? Why we use mercury a lot in some applications, for example, in thermometers. Have you ever wondered why we use mercury and not alcohol? You know why? Look at the coefficient of expansion of these materials here, because these are solids, right? So all of them are very low, except these two. Well, ignore air and helium. These are gases, right? Gasoline, glycerin, and mercury, right? Gasoline and glycerin, I mean, gasoline is very dangerous, right? And glycerin as well. So mercury, which is also toxic, but it has a very high coefficient of expansion. So it will make the column, right, based on this equation. The temperature difference doesn't have to be so high to have a change on the column. So that's the sensitivity of the thermometer. If you have a thermometer with mercury, the sensitivity of mercury is higher than other elements, like alcohol, for example, right? However, if you want to make it even more sensitive, you will have to use gasoline, right? And that's a question that we have later on. Now, why do we have linear and volumetric on volume or even area? Because you have thermal expansion for solids, and solids have area and volume. Now, the area is, for example, of a square is L squared. After thermal expansion, this is what happens with the length. They both increase. If you multiply the polynomials of these expressions, you get this. Now, alpha and delta T, especially alphas, are very small. So if you square the coefficients, this is going to be very close to 0. So you cannot remove this and you stick with this. All right. So basically, the area change, right, is equal to, or I can write it on the board, it's not here, I think, yeah. So your delta L if you're looking just at linear expansion, delta L is initial L, alpha, the coefficient of linear expansion, change on temperature. But if you're looking at change on area, that's your initial area, twice the coefficient, so it doubles, change on temperature. So sometimes they call this a gamma factor. All right. And in volume, for delta volume, is the initial volume free alpha delta. Okay. So 1, 2. All right. So solids expand. Their sizes, their volumes, and areas expand, which makes sense. So you have here, right? You have a washer, which has an inner radius, it has an inner and outer radius, right? If you hit them, every dimension increases. The inner radius and the outer radius increase. So the area will increase. Okay? Here it is, right? That's the volume. And here is the volumetric. For liquids, it makes sense that we talk about volumetric because a liquid inside a thermometer is occupying a volume. So if you heat up a container with a liquid, the liquid will expand. And it will expand by the volumetric expansion. So that's why you have the coefficient of volume expansion. All right. So I think I already said this, right? If you want to make a more sensitive thermometer, which one will you use? Which one has the highest coefficient of volume expansion? in the liquids. Gasoline. The higher this value, the more you're gonna see an expansion. So more sensitive. So it will have to be gasoline. All right. What about that? If you have two spheres made of the same metal, the same radius, one is hollow, one is solid, the same material though, which sphere expands more? If they're of the same material, both expand the same amount. Because the thermal expansion depends on three parameters: the temperature difference, the coefficient that depends on the material, and the initial size. And they both have the same size. Okay? So that's the effect of temperature in a solid. Well, there's not much to say, right? For a solid, or in this case, also for liquids, temperature differences, they cause thermal expansions. That's an application of both temperature and the state of matter, the characteristic of the state of matter. It can be mercury, glycerin, alcohol, or in a solid, aluminum, iron, right? Depending on the type of element, you will have a different rate of expansion. Okay. Now let's review. Yeah. So temperature is a parameter that is used a lot to study gases. And eventually we're going to use it to study the idea of heat. And today we're also going to see the idea of internal energy. Like I mentioned, right? There are a lot of effects of temperature. You've seen a few already. But the main thing about temperature is that it injects, right? If you increase the temperature of a gas, you are increasing the speed of the particles, right? Because temperature is a measurement of the kinetic energy of particles. So let's introduce, or reintroduce for some of you, ideal gas law. An ideal gas is a collection of atoms or molecules that are moving randomly, and there are no forces, long-range forces on each other. Okay? There's only collisions with a container. So to study an ideal gas, the first thing that you need to remember is that we need that number there. What number is this? You guys should know. What is this? How do we call this? Nobody remembers? That's the Avogadro's number. There should be a 3 here, 6.023, but they're running just to 3 suffix. So 6.02 times 10 to the 23 particles per mole. We use that number to know the number of particles of a gas, for example, or to determine the mass of an atom. How? Well, you're going to see. We also define this. Does anybody remember what N stands for?
Moles.
Yeah. Number of moles equals to mass over molar mass. For example, if they give you a solution, or if they give you carbon dioxide, 40 grams, you find the molar mass of carbon dioxide, mass over molar mass will give you a number of moles. Because molar mass has units of grams per mole. So I'm going to erase the board because I'm going to have to use it at some point, all right? So these are values that some of you remember, right? You've seen before. Now, the units are gonna help you to determine some of the equations. Like when we did dimensions in chapter 1, I told you that at some point was gonna be useful. You see, the Avogadro's number is in units of particles or molecules per mole. And mole is mass over molar or atomic mass. Atomic mass is in units of grams per mole. So my mass is in units of grams. Grams over grams per mole give you mole. Well, there you are, right? Perfect. So I can find the number of particles in a gas if I have the number of moles n. This is in mole. If I multiply number of moles times the Avogadro number, you are doing particles, number of particles per mole times mole. So Na is what we call N. This is number of particles. I'm just showing this because you're gonna see those equations, and sometimes it's good to know how to prove. Okay, so if I got number of moles times the Avogadro number, which is a constant, I get capital N, number of particles. Right? You can also find look at this and look at that. You see, particles is not really a physical unit, it's just number of particles. So what do you want to find the mass of an atom? Have you ever wondered, like, can you find the mass of an atom? Like, for example, and there's a problem in the assignment, huh? Like a question, when you're in a problem. If you want to find the mass of the helium atom or hydrogen, well, do I know? Look at this. Grams per mole, particle per mole. Grams per mole over one particle per mole, one atom, right? I get grams. So to find the mass of an atom, I can just make the atomic mass of the element divided by the Avogadro number. I don't know how many of you knew that, but if you didn't know, then you have it. And I know the atomic mass of helium is about 4 grams. It's not about, it's exactly 4 grams per mole. And this guy is particle per mole. So moles will cancel and then you get in grams. A very small value, as you will expect. You're finding the mass of the atom of helium. Really nice, right? What you can do, right? So look at this, look at that, and look at this. These fractions, they have a meaning. Okay, the other thing that I want you guys to remember is the AMU. 1 AMU, atomic mass unit. Does anybody remember what's the value of 1 AMU? Nobody remembers? It's basically the mass of the proton in grams. 1.6 times 10 to a negative 24 grams. 1.67, but in 266, 1.6. We normally say that's like U. So 1 U is equal to that. That's not mu, that's not correct, that's U. All right, atomic mass unit. So guys, the periodic table, right? There are things that you should know, like atomic number, atomic masses. You are going to be given, but for example, the atomic mass of carbon, 12. The atomic mass of helium, 4. Right? Uh, the atomic mass of oxygen, 16. Things like that is good to know. All right. What's it say? It says that 1 mole of any substance is the amount of the substance that contains as many particles as 12 grams of carbon 12. Why 12 grams of carbon 12? Well, because we can find the mass of carbon 12. And I show you that, right? Multiply, well, in this case, the mass is 12 AMU, which is a U there, times the Avogadro's number. This equation I show you already. The mass of an atom is the molar mass or atomic mass divided by the Avogadro's number. Oh, there it is. That's the example I just did. Once again. So that's the mass of the helium atom, by the way. Okay. If it's 1 atom, grams per atom. All right. So you will need your M, how it relates to molar mass, Avogadro's number. All right. Any questions, by the way, guys? Look, you're going to be given all these constants, but as a student, especially if you're going to go into engineering or science, there are numbers that you should know. The Avogadro's number, AMU, some of the atomic masses, and yeah, I mean, some of those values, for sure, you should know. Okay, so ideal gases, right? Let's go back to that. We need some of these parameters to study ideal gases, but we also need to remember Boyle's law, Charles' law, Gay-Lussac law, right? If you remember, Boyle's law PV is constant, right? Charles' law, V over temperature, is constant. And Gay-Lussac, P over temperature is constant. If you combine these three, you get PV equals to a constant NT, where N is moles and R is the ideal gas. So this is the ideal gas equation. What's R? 8.31 joules per mole per Kelvin. I told you it's going to be different. You guys in chemistry, you do 0.0821 liters atmosphere per mole per Kelvin. We use that in physics, 8.31 joules per mole Kelvin. What's P? P is pressure, V is volume, T is temperature. P has to be measured in pascals, volume in meter cube, temperature in kelvins. because look at the R, as Kelvin said. All right? So that's the ideal gas. That equation shouldn't be new. That's something that most of you should have seen. That's also in the slides. Okay? So you see there is a gas inside a piston there. You can increase the pressure. So you increase the temperature by closing the piston, right? By moving it. So okay. So now let's use some of these equations. You have it in there, but let me show you here. So you see, in physics, because we go into the theory of gases, not just the overall gas. That's good to study the overall gas. The amount of moles, you have the temperature, pressure, volume. But if you want to study the particles in a gas, I need this. So I can write this equation using this. PV, instead of number of moles, I have number of particles over the Avogadro number, RT. Now, R divided by T, sorry, R divided by NA, that's a full constant. We have a name for it. R divided by NA give you 1.38 times 10 to a negative 23. That's the Boltzmann constant. And so then I rewrite PV as number of particles, Boltzmann constant times temperature. This is the equation that we use a lot in kinetic theory of gases. Because eventually we want to study the kinetic energy of the gas and the kinetic energy of the particles. You see the container has a gas. The gas is made of particles. And guys, you're going to hear this again next semester. But these particles are moving at in random motion. We can find what we know as the root mean square velocity of the particles. It's basically the average velocity of the particle. Okay, of the particles. So if we find the average velocity of the particle, we can find the kinetic energy of a particle. And then, if we multiply by n, we can find the kinetic energy of the gas, which is, in the case of an ideal gas, is the internal energy of the gas. So basically, and I'm going to show you the breakdown in the slides. We have that. We can write the let's see if I want to follow this properly. Yeah. We can write that for a particle, for a gas particle, the kinetic energy of one particle of gas with mass m with root mean square velocity v, that's why I write it like that, is equal to 3/2 of the Boltzmann constant times temperature. using that and the definition of, because remember, K, this is K, is R over NA, right? And you know that mass can be found using the number of moles and the Avogadro's number, right? So that's where we get that. So I can find my root mean square velocity, which is the square root of free kb temperature over the mass. But like I said, we have these parameters, right? We have that mass over molar mass is number of moles, and we have that N over the Avogadro's number is also number of moles. That's number of particles, right? And that's the mass. So if I substitute, this is M over molar mass. So my M is N molar mass over Avogadro's number. And by using my Kb, which is R over NA, I can find my root mean square velocity just like this. The square root of free RT over the total mass. This is a total mass of the gas. All right. So you can either use the mass of one particle. This is for one particle. All right. Can do that. And then we can find the total kinetic energy of the gas. So we have that for one particle, the kinetic energy is 3/2 kb Boltzmann. That's the equation. For one particle, you can just use that, guys. And we're going to do an example. But for the total gas, the total Ke of the gas, Ke tot, 3/2 of N, right? Total number of particles, kb temperature. But we know that NKB, right? We know that KB is R over NA. So we can put that in here. And N over NA is number of moles. So using these two, my total energy of the gas is 3/2 N KB over KB is R over NA. Yeah, okay. 3/2 of N R. Right, your N is NNA, and NA times KB is R. So that's the total kinetic energy of a gas. That's the root mean square velocity of one particle there. And for an ideal gas, this is also known as the internal energy. Okay? That is kinetic theory of gases. That's the main idea of this chapter, though. It's introducing first the idea of temperature, how it affects solids and a little bit liquids, but then eventually how we can use it to determine some properties of gases, particularly ideal gases. All right, you have the ideal gas equation there. You have a variation of it. Well, I have it here. And then the internal energy, kinetic energy of the gas, and the root mean square velocity of a particle. And by the way, this, right? This is the kinetic energy. So this is important. The kinetic energy of one particle in a gas. See that. The difference is that for the total gas, I multiply by the total number of particles, n. So this becomes this, basically. All right? All right. So we have time. Let's do a couple of examples. So tomorrow I'm going to be doing problems on gases. All right? Let's see. Start with a simple one. Let's find the average kinetic energy of oxygen at a given temperature. And you're gonna realize, guys, that for ideal gases, right, the kinetic energy for one molecule, it doesn't depend on the number of molecules. It just depends on the Boltzmann constant and the temperature of the molecule. Okay. For a gas, we do need that. So calculate the kinetic energy of one molecule of oxygen at 270 kelvins. So the temperature in these equations, by the way, guys, have to be in kelvins. So to find the kinetic energy of one molecule, you just use the equation 3/2 kV times the temperature. It's just one molecule. 3/2 1.38 times 10 to a negative 23 times 270. Okay? If you do the math, you get about 5.60 times 10 to a negative 21 joules. So very little. Doesn't make much sense to talk about the energy of one particle, but then you have it. It will make sense if I want to find the speed, right? So how will you find the speed of oxygen? Right, let's expand on this question. So we have for one particle this. I need a mass of the oxygen molecule. And you already know how to find them. The mass of any molecule or atom, in this case of oxygen, will be the molar mass of oxygen divided by the Avogadro's number. So let's use that equation as well. I'm going to find the root mean square velocity of the particle. So I only need a mass because I have K and the temperature. So the mass of oxygen, of the oxygen molecule, well, O, the molar mass is, the atomic mass of oxygen is 16. O2 will be 32. So 32 grams per mole over 6.02 times 10 to the 23. In this case, you can say molecule per mole. Yeah, let's do molecules per mole. Mole will cancel. And then we have the small value, right, of that. Let's see. So 5.32 times 10 to the negative 23 grams. My Boltzmann constant is in the metric is going to be with kilograms. Temperature is in kelvins. So I need it in kilograms. So this will be 5.32 divided by 1,000, 10 to the negative 26 kilograms. So now I can replace that on the equation. The root mean square velocity of the oxygen is equal to the square root of 3 times 1.38 times 10 to the negative 23 times 270 divided by the mass, this. All right. Right? Yeah. Yeah, because the Boltzmann constant is joules per Kelvin. So the Boltzmann constant, by the way, guys, KB, is 1.38 times 10 to the negative 23 joules per Kelvin. So I need my Boltzmann constant in joules, I mean, my mass in kilograms. So 10 to the 3, 10 to the, okay. That, and that. Okay, so let's do 3 as 1.38 times 27 divided by 5.32. I get 4.58. So this is about 458 meters per second. That's the speed of the oxygen. Right? And you have it. All right. So we'll do more problems of this next class, guys, or tomorrow. And I might start introducing the idea of heat. That's going to be for sure on Thursday. So we're going to finish we finished chapter 10 today, but we're going to do a bit more tomorrow, like a review. And then we will do heat and what you guys did in the lab yesterday, calorimetry. That's all going to be done at the part tomorrow, mostly on Thursday. Okay, so up until what we do on that class on Thursday, that will be for the take-home exam, all right? So you already have a few topics. You have gases, ideal gases, right? This, static fluids, Bernoulli equation, and calorimetry. That will be also. So the exam won't be that long, but it's all these new topics, all right? The last topic that we're going to do next week will be thermodynamics. Basically, in there, we're going to combine some of this. We're going to look at processes, right? Pressure, volume, pressure, temperature. And yeah, that will be the end of the course. Are there any questions, guys?